Now we move on to the second colligative property, that is boiling point elevation. Okay, now you know what is the meaning of boiling point, and elevation means you're going to bring about the raise in the boiling point. Okay, now what is the definition of boiling point? It says that when the temperature at which vapor pressure of liquid becomes equal to the atmospheric pressure is when you get the boiling point of a particular liquid. So I'll just write it here. Temperature at which vapor pressure of a liquid becomes equal to the atmospheric pressure. Okay, atmospheric pressure means the pressure which is already present outside, right? And vapor pressure is, by now you know what is the meaning of vapor pressure, right? It is the pressure which is exerted by the gaseous phase of a substance when it is in contact with the liquid or solid, right? So the definition of boiling point is temperature at which vapor pressure of liquid becomes equal to the atmospheric pressure. And I told you the meaning of elevation is what? We are going to bring about a raise in the boiling point. Now, how is this going to be done? So, how is it done? So, this is the question that I am asking you all. Now, what you are going to do is, the boiling point of a solvent is elevated, or you can say it is raised, by adding a non-volatile solute to it. Now, how is that possible? Now, we know that solvent has a particular boiling point, right? Solvent is a liquid which is going to have a certain boiling point. Now, if you are adding a non-volatile solute to form the solution, then what is going to happen? Non-volatile solute, because it is non-volatile, it is not going to contribute to the vapor pressure, right? Non-volatile solute, the bonds, the intermolecular forces of attraction, they are going to be very strong. So the boiling point of that non-volatile solute is going to be more. So if you are going to add non-volatile solute to a volatile solvent to make up the solution, then you can increase the boiling point. Okay, so in this case, the non-volatile solute is going to boil at a temperature which is going to be higher than the boiling point of pure solvent, right? So what are we going to do here? Okay, we are going to take a non-volatile solute, fine, and we are having a pure solvent. Now, of course, pure solvent is going to evaporate. Okay, so of course it has some boiling point. Okay, and even this non-volatile solute, it is not going to evaporate, but it is going to have a boiling point, but it is going to be higher when you compare it that with the pure solvent. Okay, why? I just now told you the reason, because the intermolecular forces of attraction between the molecules are going to be very strong. So in order to break those intermolecular forces of attraction, we need to apply more heat, and if you're applying more heat, then the temperature is of course going to increase, giving you a higher boiling point. So you are adding a non-volatile solvent to a pure solvent, and hence this both combining together to give you a solution. Okay, now here we are going to take T naught B. Okay, T naught B is going to be the boiling point of our pure solvent, and TB is going to be the boiling point of solution. So now if you compare this, which one is going to be the highest, or boiling point of solution is going to be greater than that of pure solvent? I told you pure solvent is going to evaporate faster. So if it is evaporating faster, means its boiling point is going to be less, and boiling point of solution is going to be more. Why? Because you have added a non-volatile solute to it. So can I write it as TB, it is greater, or you can say boiling point of solution is greater to that of T naught B, that is boiling point of pure solvent, right? So now this boiling point elevation, how are you going to define the boiling point elevation? So it is the difference between the boiling point of solution and that of pure solvent at constant pressure, or you can say at any constant pressure, is called boiling point elevation. Boiling point elevation, and this boiling point elevation is represented by delta TB. Okay, TB means it is the boiling point. Fine. So how are you going to construct an equation for this? So right here, boiling point equation, that is delta TB. It is a difference means a minus sign is going to come. So it is a difference between the boiling point of solution, and which is the boiling point of solution? TB. So TB minus to that of the boiling point of pure solvent. So T not B. Okay, so this is your first main equation. So this is how the boiling point elevation looks like. So this is the equation for boiling point elevation. I hope this is clear. Now I shall explain you the diagram for boiling point elevation. This graph represents the vapor pressure temperature of pure solvent and solution. The x-axis represents the temperature and the y-axis represents the vapor pressure. Now, if you look at curve CD and curve AB, then the curve CD represents the vapor temperature curve for solution, and the curve AB represents the vapor pressure temperature curve for solvent. You can check from the graph here. The vapor pressure temperature curve for the solution lies below the vapor pressure temperature curve for the solvent, that is AB. Now, if you look at the point of intersection for AB and CD on the y-axis, that is at a pressure of 760 mm, okay, and if you look down there on x-axis, then that represents the boiling point of the solvent and the solution. You will observe that the boiling point of the solvent is less as compared to that of the boiling point of the solution. Now, if you look at the curves, then it is said that we need to increase, or we need to heat the solution at a higher temperature. Why is this so? Because we know that when a liquid boils, it attains a pressure, or its vapor pressure becomes equal to 1 atmospheric pressure. Okay, so if you look here, the vapor pressure temperature curve of solution is below to that of solvent, right? So we need to heat the solution more as compared to that of solvent, so that its vapor pressure becomes equal to that of the atmospheric pressure. And why is that so? Because I told you, when we add a non-volatile solute, the boiling point of the solution is going to increase. Okay, and here you can see the boiling point curve, or the vapor temperature curve of solution is below to that of solvent. So we need to increase the temperature by heating the solution. Now we move on to the boiling point elevation and concentration of solute. Boiling point elevation and concentration of solute. Okay, now you know how the boiling point elevation is represented. It is represented by delta TB. Okay, so the boiling point elevation that is delta TB is found to be directly proportional to the molality of the solution. Okay, so the boiling point elevation is directly proportional to molality, and molality is denoted by small m. Molarity is denoted by big M. Okay, so it is found to be proportional to the molality of the solution. So can I write as delta TB is directly proportional to that small m, right? Now I told you, if I want to remove this proportionality sign, I need to put an equal to sign along with a k, right? So what it will become? Delta TB. Now I am removing this proportionality sign, so hence equal to k m. Okay, and here do not forget to mention B. Why? Because we are studying boiling point elevation. Okay, you can put the number 2 for this equation. Now this KB here is called as the proportionality constant. Proportionality constant, and it has 3 names. Okay, the first one is boiling point elevation constant, boiling point elevation constant. Then the second one is molar elevation constant. Okay, this is OR. And the third name is, it is also called as ebullioscopic constant. Okay, so this KB here, it is called as the proportionality constant, and the 3 names given to those proportionality constant are boiling point elevation constant, molar elevation constant, and ebullioscopic constant. Now if we take this molality as equal to 1, if I take m is equal to 1, then what form this equation 2 is going to take? So then equation 2 will become what? I'll just write it here again. Delta TB is equal to KB M. So if I take this m is equal to 1, then I'll get it as delta TB is equal to KB. Okay, so how are you going to define this ebullioscopic constant? So ebullioscopic constant is the boiling point elevation produced by 1 molar solution. Okay, so what did we do? We took the molality as 1. So substituting m is equal to 1 in that equation, what did you get? Delta TB is equal to KB if m is equal to 1, right? So you are getting the definition of this constant now, that is the ebullioscopic constant. So that is what? It is nothing but the boiling point elevation which is produced when you take the molality of solution as 1. Now what are the units of this boiling point elevation? Okay, so the next topic is units of boiling point elevation. So you take the second equation again. Okay, this is our equation. So if I bring KB on this side, then what is going to happen? The delta TB is going to go up and the molality is going to remain down. Now here this delta TB, so that is the temperature of boiling point, right? So here temperature is measured in terms of Kelvin, and Kelvin is represented by capital letter K, and molality is measured in terms of mole kg inverse, right? Now if I want to take the part which is in denominator up, then this k will remain as it is because it is in the numerator position. What will happen to this? Kg is going up, so that inverse is now going to get cancelled, and mole is going to go up, but because there was no negative sign, so now this is going to get the negative sign. So you can write the unit in this way or even in this way. Okay, so this was the boiling point, elevation and concentration of solute, and the units of boiling point elevation. Now we are going to study how to calculate the molar mass of solute from boiling point elevation. Molar mass of solute from boiling point elevation. Okay, now again we are going to consider our same equation 2, that is delta TB is equal to KBM, right? So you need to keep this equation in mind. Now we are going to prepare a solution. So how are we going to prepare a solution? We are going to take W 2 gram of solute having molar mass because it is solute, it is going to be M2 dissolved in W 1 gram of solvent having molar mass M1, right? Now because we are calculating the molar mass of solute, we need to know the formula of moles of solute. Okay, so we know moles of solute, or you can say mole. When you calculate the number of moles, the formula is weight upon molar mass. Okay, weight upon molar mass. And if you look here, because we are calculating for solute, so solute is W2 and M2, so this is going to be W2 upon M2, right? Now the next step is we need to calculate the mass of solvent. Okay, mass of solvent in kgs. Okay, we already know it is W1 gram. So what we are going to do is we are going to take W1 gram, and because we need to calculate in kgs, we are going to take it as 1000 grams upon kg. So here I can calculate, I can cancel this G and G. So what are we left with? W1 upon 1000, and let the kg go up. Okay, so this is what we are left with. Now you need to put in the formula of molality. So molality is denoted by small m, and what is the formula for molarity? Moles of solute upon mass of solvent in kg. So we have both the values here. Take this as A and take this as B. So substitute A and B here. So what you would get in moles of solute? You have to substitute W2 by M2. And in place of mass of solvent, that is going to be W1 kg by 1000. So what is the next thing that I need to do? Just cross multiply it. So W2 by M2 into 1000 upon W1 kg. So what is the final answer that I am getting here? 1000 W2 upon M2 W1. Oh sorry, I forgot to mention mole here. This is going to be mole. This is going to be mole. So here you will get so you already have mole here. So it is going to be 1000 W2 mole and then M2 W1 mole, and because this kg is down and I am shifting it up, so it is going to get the negative sign. Now you are going to substitute this value of this small m, that is molality, in, take this as C. Okay, so you have to substitute this value here, the one which we derived now, in equation 2. So what is our equation 2? Delta TB is equal to KBM. So delta TB is equal to KB will remain as it is, and in place of M you write this 1000 W2 M2 W1. And now if I want to calculate the molar mass of solute, then remove this M2 out. So if I remove M2 out, what are you left with? So write this term as it is, that is 1000 W2 KB, or you can even write KB or 1000 W2 upon this will come down here, that is delta TB left with W1. So this is the formula that you will be using to calculate the molar mass of solute from boiling point elevation. I will just explain it this to you again in short. Okay, so we are studying molar mass of solute from boiling point elevation. You are going to consider the boiling point elevation equation, that is delta TB is equal to KB dot M. Now this is nothing but the product sign, multiplication. Now we are going to prepare a solution. How we are going to prepare a solution? You are going to take a solute and dissolve in it solvent. So W2 gram of solute, which is having a molar mass M2, you are going to dissolve it in solvent having a weight W1 and molar mass M1. Okay, now we know the formula for moles of a substance, it is weight upon molar mass. You are calculating the moles only of solute because we know the formula for molality is moles of solute upon mass of solvent in kg. So first step is you are going to calculate the moles of solute. So that is going to be W2 upon M2 mole. Next we need to calculate mass of solvent. We know it is W1 grams, but we need in terms of kg, right? So W1 gram upon 1000 grams per kg. So this grams here is going to get cancelled. So you are left with W1000 and kg, right? Now both these values you are going to substitute in the formula of molality. So molality is moles of solute upon mass of solvent in kg. So W2 upon M2 mole, sorry, this mole will come up. Now I have written it in this form, that is why I have written the mole here, but it should be actually W2 upon M2 mole. Okay, because I have written it here in one line, that is why I have written mole here, but you write it in this way. Mole is up here upon this solvent, mass of solvent, that is W1000 by kg. Okay, now next is what? You just have to do the cross multiplication. So W2 upon M2 mole into 1000 will go up, W1 and kg is going to come down. Just multiply this. This is simple mathematical relation here. Okay, so 1000 W2 mole upon W1 M2. Kg is down here because it is going up, that is why I have written -1. Okay, now this value that you have got for M, you are going to substitute in your first equation, that is delta TB is equal to KB dot M. So what are you going to get? Delta TB is equal to KB will remain as it is, and in place of M you are going to substitute this value, that is 1000 W2 M2 dot W1. Okay, now we are calculating the molar mass of solute. So you are going to remove M2 out, so this term will go in place of M2. Baki sub is going to remain same. There is only exchange of these two groups here.